Good morning. I'm Jeff Hammond with IGSHPA, Executive Director. I really appreciate your attention today. We have a Dig Deeper with Richard Crisp of Fernox. I'll introduce him in just a moment. Before that, I have a few slides to update everyone on IGSHPA, and then we'll get started on this presentation. It's an exciting one today on inhibitors in heat transfer fluids, at least exciting for me anyway, but I like that kind of stuff. All right, so with our introduction here, I just wanted to remind everyone that we do have a new member portal. If you haven't been there yet, go to igshpa.org and there's a members login that will give you access to the member portal. A lot of great information there. Once you're on that portal, you'll find quite a bit of information. There's a menu on the left-hand side. One of the best resources is called Member Portal Resources. That's where you'll find member-only information, some calculators, a lot of really good information there. So check that out if you haven't been to the member portal already. A reminder on the conference, it's coming up in December. That seems like a long way away, but it's really going to be here before we know it. This year, we're partnering again with NGWA, National Groundwater Association, and we'll have actually really good attendance. It's looking based upon the preliminary numbers that we're seeing. So that's just great. We have some sponsors already, and in fact, they're filling up quickly. So if you'd like to be a sponsor, you want to make sure and get that in pretty quickly. Same with the booths. We have almost all of them filled. Last week, we made some changes so that we could add a few more booths. We separated a 20 by 20 booth into 4 smaller 10 by 10s. So make sure that if you want to exhibit, you get that in now. Those are going pretty quickly. As far as CEUs go, you will get points towards your CEUs for this webinar. Just make sure that you send an email to the IGSHPA account. You'll find IGSHPA logged into this webinar, and just send in your email address and your name. We'll keep track of those points and notify you when you have half of a CEU. When you recertify, then you can use these webinars as part of those points. Some housekeeping. Once we get started, if you would, please put your questions in the chat. At the end of the presentation, I'll read those questions, and then Richard will be able to provide answers. So that will just kind of keep things moving right along. Please mute your microphone, and that way we won't have disruptions while Richard's doing his presentation. I do have a disclaimer and potential conflict of interest statement that I'd like to read, and then we'll get started. The upcoming presentation represents the opinion of the presenter and does not represent any official position, opinion, or endorsement of any products or services by IGSHPA or its members. IGSHPA town halls and Dig Deeper webinars are for member updates and education on the latest information in the geothermal heat pump industry and are not meant to endorse one technology or brand over another. It is the presenter's responsibility to disclose any conflict of interest or position that may arise in the content of this webinar. I'm going to stop sharing my screen. I'll read a quick introduction here of Richard Crisp. Feel free, Richard, to go ahead and share your screen. Richard Crisp is head of chemistry at water treatment supplier Fernox, joining the company in 2015 after previously having worked as a medicinal chemist in the pharmaceutical industry. Since then, he has overseen the development of new products and the ongoing improvement and support for existing products. He has also supported the business and wider industry with technical support and contributions to standards and guidelines both in Europe and North America. Richard joins us from the UK, and we certainly appreciate late in the day that he's giving this presentation to IGSHPA members. So with that, I'll turn it over to Richard. Thank you very much for joining us today.
Can you all hear me okay?
I hear you fine, Richard.
Great. Sorry, I'm used to Teams and my unmute button disappeared, so I was just checking I wasn't talking to myself. So thanks, Jeff. Good morning, everyone. Very pleased to be with you today talking to IGSHPA, talking about something which is very important to Fernox as a company, to me in my position as head of chemistry, which might sound a bit like a sort of high school teacher, but it's effectively a research and development manager. So a bit about myself. My background is chemistry, and that's what I'm here to talk about today. It's not to reinvent the wheel or explain to you very basic bits of information about ground source heat pumps. I'm sure you all know just as much, if not far more, about that sort of thing. I'm here to talk about water treatment and water quality, water chemistry. That's what I do at Fernox. So I'm involved in the research of new products, of reformulating existing products to make it better, the testing, and technical support, ongoing technical support for our customers around the world that encounter different problems, and we try to form a solution for them. So,
sorry to interrupt, Richard.
Yeah.
I wonder if you might speak up just a bit, or maybe move your microphone a little bit closer. I think some people are having a little bit of a hard time hearing.
Okay, I'll just shout. Can't see anything obvious to increase that. Okay, so the importance of effective water treatment in geothermal, in ground source heat pumps. I'm largely going to talk today about ground loops. I think inside the home, the sort of the load side, I would expect that to be a bit more self-evident, but of course we can discuss that as and when. So firstly, a bit about Fernox, to give you some context to the sort of perspective and the expertise that I'm coming from today. So Fernox is a company, originally a UK company, that was established in 1964, and it was established to solve a problem with heating systems, how to keep them running efficiently, how to keep them working, how to stop system breakdown, and all the problems that can come with that. Since then, we've branched out from chemicals to filters, a variety of test kits. We also do plumbing consumables, and we're now owned by a very large American company called Element Solutions, a big brand of which is McDermott, and they're involved with all sorts of things from automotive, oil and gas, offshore drilling, metal plating, things like that. So Fernox is quite a small part of our larger parent company, and so we retain that small company feel, but we have since '64 expanded hugely, and we're now a global company. We supply into North America, into across Europe, and parts of Asia as well, and Australasia. So a bit more information. You can see some of the products there. Core technologies being inhibitors for corrosion inhibition, cleaners for cleaning, heating and cooling systems, and system filters. Now, some of these products might not be available in North America, but just to give you a sense of the portfolio we provide across the world, and the products we know about. So when it comes to fluxes and jointing compounds, we make them, and so you would expect we would have a good idea of how to clean them as well. It's anything, any technology, any product really related to wet heating and cooling systems, say hydronic heating and cooling systems. We don't tend to get involved with steam boilers or related technologies. It's all wet hydraulic systems, whether it be gas boilers or heat pumps. So we're involved with all sorts of markets, residential and commercial. We consider heat pumps as part of our renewable market, but obviously that has links with residential and commercial, light commercial, so hospitals, schools, things like that. And as I say, we try to provide any solution that may be required for those systems. So we're always interested in feedback. If you have any thoughts of things we're missing or things that we could do better, then please get in contact. Our customers, our indirect customers, are of course the people that use our products, installers, engineers that are commissioning heating and cooling systems. There's only about 60 of us in Fernox, so we work a lot through merchants and distributors. So we are available, as I say, across the world through our partners in distributors and plumbers, merchants sometimes. We also supply to many OEMs, so heating appliance manufacturers. Occasionally we do work with pump manufacturers. Anyone with a vested interest in creating a good, effective, efficient working heating or cooling system. Also large installer groups like British Gas. So I think the final slide of an introduction to Fernox, specifically Fernox USA, and you can see here we have the team. So the three guys on the left, from the left, you've got Eric, who's based on the East Coast. You've got then Jason, who's based in Wisconsin, looks after the Midwest. And then you've got Dan, I think they're all on the call, who looks after Americas generally. He's our sales director for the Americas. And then you have two English chaps on the right, one of which is me. So this was at AHR, we'll be at AHR in Georgia early next year. So if you can, please come along. And I believe we're also at the IGSHPA conference in Vegas in December. So again, please come along and say hello and have a discussion. If not, there's some contact details down there of how you can get into contact with us. So, getting to the heart of the matter, are corrosion inhibitors needed in geothermal loops? And I've been on a variety of standards committees and industry bodies where this has come up. And these are some of the reasons I've heard that it's not needed. So the system is cold. Obviously, if you think of the source side, yes, the source side, it's not going to get too warm. And some of these reasons are quite reasonable. Others I find less so. Mainly rubber tubing, obviously non-metallics. You don't have to protect against corrosion. Some people argue that the antifreeze they use is very good, or the local water. I've heard that quite a few times. I've heard people from Chicago say Lake Michigan water is fantastic. It's not needed, corrosion inhibition. I've also heard the same New Yorkers about New York water. Either way, that water contains oxygen, and that's all you need for corrosion. And also the components aren't susceptible to corrosion, which may or may not be true depending on the system. So when we look at a ground source heat pump and the materials, obviously you will have a lot of polyethylene pipework, whether it's horizontal or vertical, whether it's in a lake or underground. But you will have several metallic components, and those metallic components will be essential components for the running of the system, and also for the efficiency. It's one thing to protect a system against failure. It's another to keep it pristine enough to get that efficiency, which is why heat pumps are becoming more and more popular across the world. It's getting that COP of 4 rather than trying to pump around sludge and not getting that efficiency. So when you look at the different components, and I have to thank Jeff for some of the information here. Various brass fittings, probably a stainless steel evaporator. It's not going to be damaged a huge amount. One of the main causes for concern is the pump casings for loops, which are often, more often than not, cast iron, which is a concern even in a cold system. So when you look at the temperature, I've heard a couple of different things. I'd be interested in any thoughts you have. But I've heard essentially it can be anything from freezing to room temperature. So 20 degrees Celsius, about 70 degrees Fahrenheit, running through the pump, running through towards the evaporator. Other operating conditions which might make this system cause for concern when you're looking at maintenance and efficiencies is the flow rate. So generally, heat pump systems tend to be a higher flow rate than say gas boiler systems. So that can cause problems with mechanical erosion. Any dirt in the system, that solid can be shot around the system fast, and it can start to mechanically erode the other metallic surfaces. So I was looking at, as I say, I've been on various meetings about this and whether it's needed, how corrosion resistant cast iron is. I've seen a lot of stuff saying it's more resistant than something like mild steel, which we often have to deal with inside the home in radiators, in other components. And I've just come back from a 2-week holiday. I asked someone in my team to put in a couple of metal coupons, sort of 1 inch by 2 inches, in these jars, trying to replicate an average geothermal system, which might have 25% propylene glycol in tap water. So mains water, city water, town water. And as you can see, in 2 weeks, just at room temperature, that has gone very brown with a lot of solid in it, to the extent that you can't see the coupon anymore. I mean, you can just about see it resting at the bottom, but there's a lot of solid in there. So you could say, okay, well, is that realistic? You might be of the opinion that actually when you install it, you use deionized water, so it'll be less corrosive, which is a fair point. DI water seems to work very well initially because it has a low conductivity. But if that system isn't completely airtight, you'll get more and more air come in, carbon dioxide, that will change and dissolve in the water. The conductivity will go up and the pH will drop down because DI water has no pH buffering. It doesn't keep it at a nice neutral pH range. So regardless of the water you use, regardless of the chloride levels really, the tap water used here doesn't contain a lot of chlorides. This is really just oxygen dissolved in the water, and these jars are sealed pretty well as well, so there's no additional oxygen coming in. That is enough to cause a huge amount of flash corrosion with the initial oxygen.
Hey, Richard, can I interrupt for a minute? Your sound is really bad. Can you try shutting off your video? Like the sound.
Sorry, what's that? The
Can
sound.
you try shutting off the video, maybe?
Okay. Okay, is that a bit better?
Nah, it's the same.
Okay.
I'm sorry to interrupt, but it's really
No,
hard.
no.
Yeah.
It's not that bad for me.
Okay, I've moved the laptop a bit closer. Is that at all better?
It might be a little better.
Okay. Okay, let me know if it gets really bad. If not, I'll just try and speak slowly and clearly. I realise I've got the old British accent as well. So, okay. So in conclusion, this was just a simple test to show how quickly cast iron can corrode in a water glycol mix that you might find in a ground source heat pump ground loop. So a lot of this slide will be obvious, I'm sure, but just to go through it, problems that are caused by corrosion. You obviously form debris. That can be corrosion debris, iron oxides, copper oxides, depending on the components in the system, and also limescale debris if you use hard water, tap water, which corrosion inhibitors normally contain a limescale inhibitor as well. So certainly most of the premium ones will contain both. So if you protect against corrosion inhibition, you're protecting against corrosion, you also protect against limescale formation. But if you don't, if debris forms, that can cause component or system failure, can cause blockages in pipework. If you imagine some of the components that have narrower waterways, if you think your evaporators, small bits of pipework, coming inside the house, underfloor heating, that sort of thing. Anything can cause blockages and cold spots, which are obviously very undesirable for efficient and effective heating or cooling. So loss of efficiency, I said that before. The real USP with heat pumps over any other heating appliance is just how efficient they are, being able to generate 400% energy for 4 to 1 what you put in electricity. You can easily lose a lot of that with sludge in the system. Increased noise in the appliance. That's depending on the size of your house and the land around it, that can be more or less of an issue. Certainly in the UK where we have less space between homes, that noise will be extremely important. And so a lot of heat pump manufacturers are trying to make them quieter and quieter. If you get a bit of limescale in the pump or there's some sludge that's connected, maybe the pump has maybe there's an ERP pump involved which has a magnet in it, and so it's collecting a load of magnetic iron oxide. that's going to cause a grinding sound, and as well as eventually causing component failure, that's going to cause issues with noise as well. I mentioned before mechanical erosion from debris. Obviously, the more sludge you have, and depending on the type of sludge, if it's metal oxides, having that going around your system at a higher flow rate is going to cause some damage to the more sensitive components. And then finally, dissolved metals, which is sometimes overlooked because they might not necessarily come out of solution immediately, so they're not blocking anything up. But we've had it before where you only need a bit of dissolved copper, say, to then crash out of solution onto another metal, and then you have two dissimilar metals electrically bound, effectively plating the other metal. And it's then where you start getting pitting problems. And you can get problems even in something which is normally fairly resistant to problems like stainless steel. So a quick one on how corrosion inhibitors work. You've largely got three groups. You've got organic, anodic, and cathodic. Organic are very simple. They just bind, they just stick onto the metal and create a surface. It creates a barrier between the surface of the metal and the water. So effectively, if you imagine corrosion being a cell, an electrical cell, a circuit, that barrier stops that. Then you've got anodic, something like nitrates or molybdates, where the chemical actually reacts with the very outer surface of the metal. So it's only sort of 1 atom deep. It's not corroding away the metal. It's just forming a layer with the metal rather than entirely separate. And then you have cathodic inhibitors, which actually use calcium and magnesium from hard water. So there is some benefit if you have a good anti-scalant in a premium inhibitor, where you actually use some of the salts in the hard water to your advantage to give a bit of protection. Soft water can be particularly corrosive. And it also gives you more pH buffering, so it's also hard water is more likely to keep the pH in the range you want it, sort of 7, 8, slightly alkaline. That tends to be the best for most metals. So a couple of types you'll see. Obviously, maybe slightly off topic, but there's, I wanted to give a bit of background rather than just saying, yes, it's a good idea to have corrosion inhibitors. So these are the three main groups, I'd say, you're likely to find on the North American market, certainly. When we first looked at the North American market, there was a lot of food grade inhibitors. And what these seem to be is largely just potassium phosphate. You'll often find various states and various cities sometimes specify these or don't allow anything but food grade inhibitors. They're very simple inhibitors. Can have some issues with performance. The main issue we find, we try to formulate our product to have stability in all waters. So however hard it is, our products will be stable. They won't form a precipitate, which might settle to the bottom of pipe work and low flow areas. With anything phosphate based, you normally have a problem with hard water because you form calcium phosphate, which then comes out of solution. So you'll find in a lot of these inhibited products, which are phosphate based, they normally say it can only be used with deionized water. So obviously that may or may not be a problem if you prefer to use deionized water, if you have a good way of producing it or a cheap way of shipping it in, that may or may not be a problem. And because it's food grade, you tend to find them with monopropylene glycol, which is also food grade. And I'll come on to some of the accreditations linked to those products in a bit. Other corrosion inhibitors sometimes label themselves as organic. It's not a lie. It's partly a marketing tool, I'd say, to give the appearance of being less hazardous. As a chemist, it always slightly irritates me when you see things that are organic and plant-based and other such words, which they may well very be, but that doesn't necessarily mean they're better than the equivalent, which isn't. So they're largely based on tannins. Tannins are a sort of dark brown colour, or organic acids. Now again, you can get some very nasty organic acids. You can get some not very hazardous organic acids. So it all depends on the product, and the safety data sheet will be able to tell you a bit more about that. And then you have mixed inhibitors. By and large, most modern inhibitors, especially from Europe, I'd say, are based on a mixture of organic and inorganic. Again, can be non-hazardous, can be hazardous. All depends on the product, and you should speak to your supplier or look at the safety data sheet to make that judgment call. So this is a busy slide, so it's good that it's being recorded. I just wanted to give a few other factors where, if you're looking at protecting a heating system or a cooling system, other things to factor in to which product on the market you choose. So I've mentioned demineralized water, deionized water, same sort of thing. Effectively pure water. You can either use a product which doesn't specify like that, or there may be an additional cost or an additional time on site to reduce the deionized water, and it may be something to look out for. Any product which does say can only be used with deionized water, just have in the back of your mind that that's probably because it's not stable in hard water. And then there's other factors which I'm sure you're all, if the members, I'm sure you're the let's say the top of your game, and you're all very conscientious and take pride in doing a good job with regards to geothermal systems. So there's just a couple of other features here which ethically your companies may want to look at. Some you may decide are a big problem, others you might think that's fine. So things like nitrites, nitrates, you sometimes find that in the groundwater from fertilizers. You'll also find it in some corrosion inhibitors. There are environmental concerns. If that's disposed of incorrectly, it can cause things like algae bloom. If it's in a lake, say, you can then go to the lake the next day and it's all covered with a nice thick green layer of moss and algae. There's various other hazards potentially with those products, and you can get underdosing issues. So with some anodic inhibitors, if you underdose them, they're actually worse than if you were to put nothing in at all, because they can protect some of the metal but not other parts, and then that causes a dissimilar environment, and it can exacerbate corrosion, can cause pitting and things. Phosphates, as I mentioned earlier, very popular in the US due to they're the obvious choice if you need food grade inhibitor. More and more though, you are seeing states say point blank that you shouldn't be disposing of phosphates into the wastewater stream, because again, similar environmental concerns, they can be an issue to get out of the water system. Borates are largely something of the past. I know Fernox changed over from about 2010. There started becoming hazards associated with them, but you do still see them on the market. But that should be fairly obvious by the hazard labelling. You'll see a sort of exploding body, we call it. It's like a silhouette of a person with the organs highlighted, because it's a reproductive toxin. Biocides, this is obviously a key one for geothermal systems. Depending on your base antifreeze fluid, which we'll come on to in a second, you may or may not require that. Obviously, it's a low temperature system. You're not going to be thermally disinfecting anything, so you need to make sure that the heat transfer fluid you have is not going to sustain growth of microorganisms, which I'm sure you'll be aware cause a variety of problems, as I went through with corrosion debris on the previous slide, blockages, system failure, and you can also get MIC, which is microbial induced corrosion. Water quality, so similar in some ways to the first point about do you need deeming water, what sort of water can you put with this product. You might get some products which say can only be used with a max of 100 ppm chlorides, for instance, so something to bear in mind. pH buffering, mentioned it before, with soft water or DI water. You get any carbon dioxide from the air into the water, that dissolves in and essentially becomes carbonic acid, which then drops the pH, and you'll exacerbate that corrosion happening. So certainly cast iron is not going to last very long in a low pH in an acidic system. If you have formulated product in there, especially one with good pH buffering, you can absorb carbon dioxide from the air, just because maybe the system isn't airtight for some reason, but the product would fight that pH change and keep it neutral. Glycol stabilizers, occasionally if you've got a good source of maybe glycol or some other heat transfer fluid, a cheap source, and you don't want to buy a formulated product, that's an option certainly, but just be aware that a formulated product may have things like stabilizers in to protect the glycol from degrading, going yellow and losing that frost protection. And linked to that, can you buy the corrosion inhibitors separately? So for instance, we supply a product called Alpha 11, which is propylene glycol, and with our corrosion inhibitor F1. Now, there's nothing really to stop you getting your own glycol and then adding in our corrosion inhibitor F1 separately. Obviously, you should make sure it's a good quality, relatively pure, the color's good, etc., etc. But that's also an option if that works best for you and your company. So a bit of information, because I'm sure you probably guessed if you hadn't already been aware that picking between different products, once you think, yes, I need a product for this loop, can be tricky. And so there's a lot of different accreditations, test methodologies out there. So a very brief run through. You'll probably see this one more often than not, the NSF non-food compounds one. So this started off as an approval for food and beverage processing plants. And the idea was to certify products that could be used with incidental food contact. Seems to have taken on a bit of a life of its own. It's now routinely requested by states, by cities, sometimes enforced, to have, even if there's no chance of food contact or drinking water contact. And the specific program within the non-food compounds program is normally HT1, which means incidental food contact. There's also an HT2 for heat transfer fluids without incidental food contact. Again, most of the HT1 will be linked to the potassium phosphate. And so we were very pleased to get the Alpha 11, which is non-hazardous but not necessarily food grade, approved for incidental food contact. That was a nice thing to have achieved without having to sacrifice any of the formulation for to maintain performance. Linked to that, you sometimes see FDA approved or GRAS. GRAS is generally regarded as safe, and this is linked almost entirely to food grade. So be your phosphate based corrosion inhibitors. And then you have two test methodologies. I think they stand alone really globally. You've got an ASTM standard, which is mainly used in North America, and then you've got another NSF program, which was used initially in the UK, but it is now starting to spread. This ASTM standard D1384 is a reasonably good test methodology for testing heat transfer fluids, tests against cast iron, solder, copper and aluminium, I think. So a lot of manufacturers will quote that and will quote as they pass. Similarly, NSF CIS, that's corrosion inhibitor approval scheme. Furnos is a lab that runs that test routinely. And that's essentially, it was based originally, I think, on the ASTM standard, but instead of being for engine coolants, it was more specifically designed for heating and cooling. So we try and mimic that as much as possible. We've also got a couple of materials that we test, non-metallic tests. So we also check rubbers, EDPM rubbers, and O-ring material to make sure that the chemicals don't swell or perish in those. And then just a couple more. These are largely related to Europe. Kiwa's Dutch, but they do have a global reach. Belgiac was largely Belgium, but it's just there for information to be aware of some of these accreditations that might pop up. Some of them will say this chemical is non-toxic, and they can they'll see our formulations and prove that that's the case. Others actually come to our factories and check that we're adding the right stuff. We haven't said our formulation is something and then we're using a very cheap alternative. We are using the correct materials, correct purities. We've got a proper quality system in place, and so we're heavily involved with most of these. So types of antifreeze, various types. You've got a couple of different organics. You've got monopropylene glycol, got monoethylene glycol, and then you've got some other ones, glycerin, glycerol. Occasionally you'll see something like triethylene glycol, which has a bit more stability at high temperature. But by and large, they're the polyols. By that just means more than one OH group. And how they all work, you can see without boring you with the chemistry too much. You can see that they've all got these red oxygen atoms, and it's those red oxygen atoms which interact with the water, get in the way of the molecules, and so stop it from freezing as easily. So you then got alcohols, methanol, ethanol, and then what we loosely term as brines, which isn't just seawater. You've got acetates and formates, which are organic as well, and then you've got calcium chloride and things, which I think is used occasionally for things like ice rinks. I'll come on to the pros and cons of each here. Obviously, I should say it depends on the manufacturer. You could take a very corrosive based fluid and you could come up with some fantastic corrosion inhibitor, but actually it works better than this table would suggest. That this table has been proposed into the new CSA C448 standard for next year. So I was part of the water quality subgroup, looking at how we can give some basic information on products and looking at different properties. And so you can see it's obviously very subjective. We've tried to differentiate where we can, but you know, a good and a very good might be quite similar, but we tried to introduce some form of ranking. So you can see, so for corrosion protection, say, the glycol is very good. Alcohol's reasonable. When you get to things like acetates or formates, it is difficult to have a potassium acetate or a potassium formate solution, which is very corrosion resistant. And from the talks I've had before, excuse me, I've found that that's the case. I think potassium acetate became popular in North America, and I think it was sold as a sort of bananas and pears, but they can be very corrosive. I think how it works is acetates get into small pits and become acetic acid, and then they can cause problems. You've also got flammability issues with alcohols and toxicity issues. So all something to bear in mind. See what your state says, see what your city says, what you're comfortable working with on site, what you're comfortable if there's a leak, or are your leak prevention procedures robust enough. It's all considerations which might help you choose between a formulated product. Just very quickly, I realised we then got 9 minutes left, so a couple of bits of test equipment which can help. A refractometer is very useful at checking frost protection. So we sell one. You put a drop on the lens, look through it, and it tells you the frost protection of that system, and it tells you the percentage in glycol, whether it's propylene or ethylene. And Fairnox doesn't supply products in ethanol and methanol, but I'm sure they have a associated refractive index as well. And also test strips. Can't really stress enough how useful a quick test for corrosion inhibition is. It's now largely mandatory across across the UK, and it's going that way in Europe. But this is a very simple test we do. Measures molybdate levels, dip it into the water or the glycol, and this will tell you if you're above the minimum line or not. So thank you very much for your time. I hope that was useful. I hope you could hear me a reasonable amount. Any questions?
Thank you very much, Richard. I certainly appreciate your time. You may, if you don't mind, maybe stop sharing and turn off your camera. I hate to say that, but that may help with the audio as we're going through the question and answer period. Well, hopefully anyway, but that was really, really useful information. We have a lot of really good questions here. The first one comes from Sean. He asks, what does MPG mean?
So monopropylene glycol.
Monopropylene glycol.
Yeah, so it's essentially the most common antifreeze I think you'll find in heating systems. In a car, it will be monoethylene, but in a heating system, it's normally propylene.
Okay.
So it's an acronym for the chemical.
Okay, thank you. That's very, very helpful. Wes asked a question here. Can you overdose with nitrate based inhibitors? Can you add too many nitrates?
Not really. The main problem, as I said, was underdosing. It's just a factor you might want to consider is sometimes there are links with nitrate usage and then microbiological problems later down the line. So, you know, it contains a source of nitrogen, so it can be food for bacteria.
Okay, very good. Here's the next question from Damon. He asks, do the three different protection mechanisms cause measurable difference in heat transfer on the heat exchangers?
No, so they're only literally a molecule wide, so no, it'd be negligible.
Negligible. Okay, that's great to know. We have another question here. This is from Ruben. He asks, are biocides required if sufficient glycol concentration in systems that are stagnant for extended periods?
Yeah, it's a good question. It's something I forgot to mention actually. Well, so with glycols, over 20%, you shouldn't really be getting anything unless your system is already contaminated. There's already maybe biofilms in there. Your system should be what we call biostatic, and the reasoning behind that is over 20% glycol, whether it's propylene or ethylene, has a reduced surface tension. And that reduced surface tension interrupts with bacteria's cell wall. So no, you shouldn't assume that the system was sort of clean going in.
Okay, very good. Next question from Wes. Can you mix nitrate-based and phosphate-based inhibitors?
If the manufacturer of the product says you can, potentially.
Hey, Jeff. This is Wes. I was actually asking about nitrite, not nitrate.
Oops, sorry, nitrate.
And same thing for the overdosing was nitrite.
Okay. Yeah, I mean the overdosing was the same answer. No, you can't really. But yeah, just watch any issues of bacteria. We've had systems before where they've had a big problem, corroded through a lot of things due to biofilms, and then they've switched to a non-nitrate based inhibitor, and those problems have gone away.
We've tried to target 400 parts per million in the past, and that was based on an old IGSHPA document that we were looking at. Does 400 parts per million sound reasonable, or should we be higher or lower than that?
No, I think that sounds reasonable. That's quite a high level. We don't use nitrates in Fernand's products, so I don't have the optimum ppm to hand, but that seems reasonable. It seems quite high, but that's not a bad thing for any risk of underdosing and dilution over time. So no, I think that's fine. And I know some products are formulated with nitrites and nitrates in the same product. So no, that's not a problem.
Okay, thank you.
No problem.
Yeah, and thanks for that clarification, Wes. There's also a question here, can an inhibitor be added to methanol water mix?
Yes, it's not something we routinely test, but yes, I know many instances where that's worked very well.
Okay, great. Yeah, some people think that methanol has enough protection on its own, but I wouldn't agree with that, I guess, in my opinion, at least from experience.
No.
Tom asked the question, can you comment on the use of sodium silicate as a corrosion inhibitor?
Yes, the silicates can be very effective, but they have to be used in the right system. For a start, there can't be any aluminium, which is not necessarily an issue in these systems that we're talking about. But to keep them in solution, you have to have quite a high pH, which is why sometimes when people start mixing automotive corrosion inhibitors, they can get a lot of solids start to form, which is linked to silicates and pH change. So no, if the pH is sufficiently high, I think we're talking about sort of pH 12, so very, very high really. Then you can be okay. You just might want to watch if you're going up to that high pH that it doesn't start corroding your brass and copper.
Okay, so the pH has to be high enough in order to use sodium silicates as
Yeah,
corrosion.
to keep them in solution. Yeah.
Okay. Monica asked, actually makes a statement here, nitrates as corrosion inhibitors are forbidden since 2005 in Europe due to health hazards. Really surprised that you still use it. Any comment on that?
I mean, Fernox don't use them, but they are still routinely used. I don't know whether that's maybe a specific. I haven't come across that because I know a number of leading brands that use them. I mean, sodium nitrate as a raw material can be non-hazardous, so it can still be used in the various applications we work in. But I'd be interested to see what that bit of legislation is that Monica's come up against.
Okay, maybe if Monica, if you could maybe send us an email at info@igshpa.org, we'll pass that along. Thank you for that information. Adib asks, what type of antifreeze is Kilfrost?
Well, I not working for Kilfrost, I can't comment specifically, but it seems to be a mixture of brines and maybe other organics.
Brines and organics. Okay.
Yeah.
Okay. Very good. Monica has a comment, and it is 31 after the hour, so I guess I wasn't watching the clock. This is such good information. If you have time, we have 3 more questions. Is that okay, Richard?
That's fine. That's fine.
Okay. Thank you. Or 2 more, I guess.
The weekend.
Okay. Thank you. From our experience, Monica says you should never use silicates for geothermal application due to huge problems with microbial corrosion. Any comments on that, Richard?
Again, another interesting one. I wouldn't have thought of silicon as a metabolite for bacteria or microorganisms. But that's new to me. I wonder if it's maybe other chemicals which are mixed in, which are actually providing the nutrients there. I wouldn't have thought silicon would, but yeah, again, if you send through any other information, I'd be very interested in that. Thank you.
Okay, very good, very good. Maybe we can find out a little bit more about that. And then our last question, and we'll let you get back to your evening now in the UK. John asks, what additives are recommended to act as a biocide for bacteria such as Pseudomonas or
Yeah,
Pseudomonas?
So in heating systems generally, if I use a very broad brush answer, they tend to be non-oxidizing. If you have something oxidizing, you can run into issues with non-metallics and plastics. We use something called isothiazolinones, which I'm not expecting anyone to write that down and to spell it necessarily, but you can get a range. There's isothiazolinones. We use one called BIT. Occasionally you'll see CMIT and MIT. There's also quats sometimes used, which are quaternary ammonium compounds. I mean, probably a Google search of non-oxidizing biocides would lend itself there. They normally mention what pHs they're stable under, and most of them will have at least some activity against Pseudomonas. If you do come up against one which doesn't, you can normally get a blend with 2 active ingredients instead of 1, which closes any gaps on that activity.
Okay, very good. Well, thanks again. I appreciate your time, Richard, and thank you everyone who joined us today. Hopefully you have a nice weekend. I guess I should have paid more attention in chemistry class, huh? Take care, everyone. Thank you.
Thank you. Bye.